So we are talking about charging of a capacitor, right? The last thing? Yeah. So the equation that we came up with charging of a capacitor. Through resistor. For that one, we ended up seeing that the charge at any time is going to be the charge 1 minus e to the power of minus t over RC, right? Was that the equation? The charge at any time as it starts getting charged, this is charging process. At any time, you want to know what charge has it acquired at that moment of time, at time t. All you do is just plug it into this equation, and when a capacitor is being charged, this is how the circuitry is. So this goes through a resistor and to a capacitor. So let's discuss about this right now. That's your power supply. Let's call it the EMF. That's the maximum voltage that you can think of there. And let's say this resistance is 6 ohms. And let's say this EMF is 12 volts. And let's say this capacitance of the capacitor is something. See? So before you start the charging process, like before you turn that switch on, what's the potential difference across here, across the capacitor? Before you started charging it, before the switch is turned on, what is the potential difference across the capacitor? If I put a voltmeter across here, it will read the potential difference across the capacitor. How much is it going to be? 0. And if I put a voltmeter right here across the resistor, how much is that voltage going to be? 0. So that's how it's going to start. However, as soon as you turn the switch on, what's going to be the potential difference here? As soon as you turn it on. Huh? As soon as you turned it on. Okay. The potential difference across the capacitor depends on what factor? How much charge it has got, right? As soon as you turn the switch on, what is the charge on the plates? 0. So the potential difference will be 0. As the moment you turn the switch on, this will have nothing built into it yet. So its potential difference is 0. But you apply 12 volts. Where is it all going to be? You apply 12 volts to this and this, but this one is saying 0. How much is this going to be? 12. So if 6 ohms is getting 12 volts across it, what's going to be the current that's going to be? 2 amperes. So the current is going to be 2 amperes to start with. The current that is actually flowing into the capacitor is 2 amperes. The current is 2 amperes initially. In other words, the 2 amperes is the maximum current. But as a result of this maximum current, what's going to be the end result? It's going to get charged. As it starts getting gradually charged, what do you think is going to happen to VC? It's going to go up. Suppose this voltage goes to 4 volts. What will happen to this voltage? It will drop to 8 volts. So what will happen to the current? It will be 8 over, which is 1.5. It's 1.5. So the current is beginning to drop. But the current is still flowing. The current is beginning to drop, but the current is still flowing. So what will be the consequence? Because the current is still flowing, it will acquire more charges. That will make the voltage go further up. If the voltage there goes further up, this will come down to 4 volts. And now the current is going to drop further down. Because now 4 over 6, the current is further down. And this thing keeps going till this gets charged more and more. And finally, when this gets charged fully to its maximum capacity, Q naught. Q naught is the maximum. Once it charges to its maximum capacity Q naught, what's the voltage here? 12. And what's the voltage here? 0 volts. Since the voltage across the resistor is 0 volts, what is going to be the current in the circuit? There's no current that's going to flow. So the current is kind of dropping from a maximum value to 0. From 2 amperes is dropping to 0. And the charge across here is building up from nothing to a maximum. So that's where we saw those graphs. I don't know if I showed you. So this is a Q versus time. If that's a charge versus time graph, the charge in the capacitor initially is 0. However, how quickly is this charge growing? That's basically what we know as current, because I means dq over. So you know the charge is 0, but how quickly is it rising? dq over dt, that's a slope. So initially the line will be a steep slope. You can see the charge is building up very quickly at this rate. And the rate you already know is 2 amperes to start with. So the slope of this line is supposed to be 2 amperes. What happens after a little time? As it starts building charges, the rate at which the charging takes place also is going to go down. The rate initially was 2 amperes, and after some time it's going to be 1.5 amperes. After some time it's going, so the rate is going down, so the slope of this line is going to change, and finally it becomes, the slope becomes 0. So this is a charging process. What is this charge over here to which it builds up? Q naught. Q naught is the maximum charge it can acquire, and there you go. That is Q naught. And the slope of this line is the current. So during the charging process, the charge is going to build up to a maximum value of Q naught. And as you can see, the voltage across the capacitor also depends on the charge. Right? The voltage across the capacitor also depends on the charge. So you know Q is equal to CV. So the voltage is dependent on the charge straight away. So if the charge is going to behave like this, the voltage is also going to behave like that because C is a constant. And so the voltage graph, so the voltage across the capacitor is going to build up from 0 the same way to a max. And that is going to be the E. Right, Ethan? So the maximum voltage to which you can actually make it grow is the EMF full. When the current drops to 0, no current flows even in the internal resistance. That means there's no internal drop even. So everything goes to the EMF. Yeah.
What's the x-axis on that one?
Time, with respect to time. So even here, you can see the maximum value is, this is a slope of 0, and that's when it reaches the maximum value of whatever you applied. Now what is going to be the difference in this graph if I keep a resistance here, not 6 ohms, but 2 ohms? If I keep this as 2 ohms, what's going to be the difference on the graph?
You're going to have a higher slope.
Higher slope. It's going to be a higher slope, which means to pick up these charges is going to be much easier, much faster. So the line is going to be like this. If the resistance is lower, then it's going to be a higher slope, and look at that. You get it? If this resistance is like 600 ohms, then it's going to be a lower slope to start with, but eventually it will go there. It has to finally go to the max. So no matter what this resistance is, the maximum charge this is going to acquire is according to this voltage. Okay? Maximum charge this can go up to, is maximum voltage it can go up to is 12 volts. So you can have different rates at which it's picking up the charges. It can be slow, it can be fast. Now if you don't have any resistance at all, like you just have a wire connecting straight away to the capacitor, like the way I used to charge the capacitor, right? If nothing is connected, just straightforward, just touch it. As soon as you touch it, this will grow quickly there. That's it, over. So fast. The moment you touch it, it's already charged. It takes hardly any time for the charge to build up to that value. So this resistor is actually kind of slowing the process down. Okay, is that clear? Now, translating that graph to the current graph, what is the current that is actually flowing into the capacitor? Current versus time graph. If you want to look at the current versus time graph, you know that rate of flow of charge is current. So the slope of this line is going to be the value of current here. So the slope here is the highest positive, and so the current is the highest positive. And what is that current equal to? How much is that highest current possible?
2.
E divided by R. So this is E divided by R. That's highest current. Highest charging current is E divided by R. In this case, it is 12 divided by 6, which is 2 amperes. The highest current that you can have in a charging circuit is E over R. And what happens to the highest current? What happens to this slope as time goes on? The slope gets smaller and smaller and smaller, and finally 0. The same thing happens here. The value gets smaller and smaller and smaller and smaller, and finally 0. Finally, the current becomes 0. So starting with the current of E over R, it falls off to 0. So the slope of this line is this line. Okay? So you see how the charge is going to fluctuate. You see how the current is going to vary. You saw how this is basically charging. The whole thing, what you're seeing right here is charging. Discharging. Discharging is going to be this. We saw that yesterday. Discharging. Discharging of a capacitor through a resistor. This is how it is discharging. How can it discharge? Well, it has to be charged first of all. So let's say this was fully charged. Suppose this is fully charged. Alright? This is fully charged to the maximum voltage possible, which is E in this case. So the charge across a capacitor is Q to begin with. So it is starting from here, Q naught. When you're discharging a capacitor, the charge across the capacitor is all Q naught, full. And as soon as you connect it to this resistor R, let's say in this case 6 ohms, and this was the EMF, full voltage, which was 12, what's going to happen to the current now? The current is not going into the capacitor, it's going to go out. That's why we flip the signs. It is not a charging current now, it's a discharging current. The current is going to be changing its direction altogether. So this current is going to be flowing in this direction. So it is a current that this is a current that does not make the charge grow, but make it decay. This current is not a charging current, it is a discharging current. It makes the Q naught go from high to low. So this is the discharging current, charge. So the charge falls exponentially according to this equation. The charge falls exponentially according to that equation. Obviously the initial charge was what this had, and the final charge which will remain on the capacitor is going to be 0. Is that clear, Carl? The next thing is, let's talk about the current itself. You know how to look at this in terms of current. The slope of this line is supposed to give you the current. Now you can see that slope of that line is negative. So if you're only drawing the magnitudes, then the graph will look exactly like that. But if you're just drawing the real current, including the directions, then the current is going to be all negative. So this is a negative maximum slope, so therefore negative maximum value. And this current is the maximum voltage that it has over R. And then, of course, it's negative. And then this thing starts fading off to 0. So the current drops off to 0 from a negative value. So initial current is a negative 2 and final current is 0. So this is what happens. But you don't normally like focus on which way the current is flowing, but you know, if you're just drawing the magnitude, then you can draw the same shape. Yeah.
Last class you said that that data point was I naught. Is I naught the same thing as?
I naught is the same thing as this. Yeah, this is I naught. That is I naught. I max. Yeah.
So it's negative because it's discharging?
Yeah.
And so at the beginning it discharges a lot and then slowly.
Exactly. The capacitor is going to discharge a lot initially and then kind of fades off. Good. Yeah, this is basically a discharging graph. So the voltage across here initially is the highest, so just like that. So all the three graphs are basically going to be exponential of this type. There's only one graph that goes like this upward, which is the charging graph. Right? All right. Now the other thing that you need to focus on here is, you know that resistance is the one which changes how fast it is discharging or charging. So if you put a bigger resistance, it will take more time, right? It will slow down the entire process. If you put a higher resistance, what did I say?
You said bigger.
If you put a higher resistance, it's going to slow down the entire process. If you put a smaller resistance, it's going to speed up the charging process. It's going to be faster. So there is a timing involved in this. There's a timing involved in this. And the timing depends purely on R. And of course, it also has to do with capacitor too. And that timing is what we call as a time constant. So we're going to define what a time constant is. So we can write it down. Time constant. Now in chemistry, you must have learned something about half-life. That's also like a time constant. Like you know that every material, every radioactive substance, we'll see that later, is supposed to decay. And the rate at which it's going to decay depends on its activity. And the time it takes to decay completely is technically infinite. It's supposed to be infinite. All radioactive substances will take infinite time to completely decay. All right? The same way here. All capacitors will take infinite time to completely cut off. Just like a radioactive substance. And in radioactivity, but still there is a difference between one element and another element, right? So one radioactive nucleus will decay faster and the other one decays slower, but eventually they are supposed to take infinite time. So it doesn't make sense. All of them are infinite time, but one goes faster than the other. In order to give a time consciousness, we define what is known as half-life. So how long does it take to go to half its original numbers? So if I have 100 grams of radioactive substance, how long will it take for it to become 50 grams? That is called half-life. And then from 50 to go to 25, it's the same time. So that is a timing aspect over there. And here we don't look at the time as half-life. Instead, time constant, we call it RC, the product of R and C. So time constant is symbolized by the letter tau. That's a Greek letter. Again, you may be seeing this for the first time. It's called tau. It sounds like tau, T-A-U. And this is a Greek T. If you look at all the symbols, you'll see this symbol. It may not be exactly the same shape. It may be more like that or something. Okay, but it's a Greek T. It's basically this. If you knock off the top part of this, it's almost like tau. Okay? So this is tau, and this is specifically used to denote time constant, only time constant. So that Greek letter is only used for time constant. And what is this tau? Tau is a certain amount of time, which is actually the product of R and C. As you can see in this equation, time is coming on the top. RC is coming in the denominator. That means this and this must have the same units, right? Otherwise, it won't be a pure number. The top has to be a pure number. It's like e to the power of minus 1, e to the power of minus 2, minus 3. It has to be a number. You can't have a variable sitting there. So time and RC are actually the same units, which is basically seconds. If you want, you can check it out. What's the unit of resistance? Yes, but what is ohms in basic terms? Can you flip the pages backward and give me that? I think I've discussed that. What is ohms in basic terms? Go back and fetch it. What is ohm in basic terms?
Kilograms,
Yes.
meters squared, amperes squared, seconds to the -3.
Okay, now tell me what is C. Go back to C. When I define capacitance and all that, I must have definitely given you the basic terms, unit of capacitance. Tell me the units. No.
kg.
Yeah.
Isn't it kg to the negative first, and to the negative seconds,
Okay.
amperes to the negative second, and seconds to the fourth?
There you go. So what is RC then? Product of these two. So it's kilogram meter square ampere square second to the power of minus 3 times kilogram power minus 1 meter power minus 2 ampere minus 2 and seconds to the power of 4, and that is going to be what?
Seconds.
Magic. That's why I gave you those things earlier, so that I'll get back to it. So what is the product of RC supposed to be in? Seconds. And that's why you see time here and RC here. So basically the product of R and C gives you time. The product of resistance and capacitance will give you time. Okay? So let's go back to that equation. At t equal to 0, what is Q equal to?
E.
At time t equal to 0, what is Q equal to?
Q.
Q naught. Right? That is just before discharging. If you put 0 there, e to the power of 0 is going to be, yeah? So you have initially, before discharging, at time t equal to 0, Q is equal to Q naught. Same thing. At t is equal to RC, when the time is one time constant, which is RC. What's going to be the equation? It's going to be Q is equal to Q naught e to the power of minus RC upon RC. That is, Q is equal to Q naught e to the power of minus 1, which basically means Q is equal to Q naught over E. So when the time is one time constant, the charge that remains will be just 1/eth of its original value. One eth. Like 1/3, 1/4, 1eth. What is E? 2.702, something like that, right? If you type in e to the power of 1 on your calculator, it will tell you what it is.
2.718.
718. 7? Oh, 2.718? Yeah. 2.718 something. So what is going to be the charge after one time constant is going to be 1/eth of Q naught. 1/eth is what percent? What is 1/e in terms of percentage? Like what percentage is remaining? What is 1/e in terms of percentage? What is 1 over 2.718?
37%.
Almost 37%. That means this Q is going to drop to almost 37%, which is roughly here, after one time constant. This Q is going to drop to Q naught over E after one time constant. You get it? What is going to happen at T equals to 2 tau, which is basically 2 times RC. Then what happens? Q is equal to Q naught e to the power of minus 2 RC over RC, which is Q equal to Q naught over E squared. Because e to the power of minus 2, and that's E squared. And what is this? This is basically 1/e of Q naught over E, right? Isn't this 1/e of Q naught over E? So what does it mean? 35% of this, 37% of that is going to be the new one. So this number here is Q naught over E squared. So for 1 RC, it drops from here to here. For 2 RC, it drops from there to there. And you know what's going to happen after that. So after 3 RC, it's going to be Q naught over e to the third. And after 4 RC, it's going to be Q naught over e to the power of 4, and it keeps going like that. So you can see it's kind of dropping off every time by almost 63%. So a drop off from here to here is like 63% of what was here, and 63% of what was here is here, and 60% of the next one is here, and from there it keeps fading off like that. That's why it's an exponential fall, because you're talking about Q naught over E, Q naught over E squared, Q naught over E to the power of 3, e to the power of 4. It's an exponential decay. Same sort of decay you'll see in radioactivity as well. So, if you're asked a question, the charge goes from one value to another value, how long did it take? Right? How long does it take for a charge to go from this value to that value? So what you do is, numerically, this is what you do. Alright, so let me give some numbers. If R is equal to 6 ohms, as in our example, and let's say capacitance is equal to 2000 ohms, 2000 microfarads. Or let me put resistance differently. 6 kilo ohms. Okay. So if the resistance is 6 kilo ohms and if the capacitance is 2000 microfarads, can you tell me what the time constant is? What is the time constant? Yeah. 12 seconds. All you do is multiply R and C. You multiply R and C, you get 12 seconds as your time taken for this capacitor to drop from here to here, to drop from the initial charge it had to 1/e of it. The same way for voltage. Starting with the voltage of 12 volts, how long does it take for it to go from 12 volts to 12 volts over E? That is called one time constant. Okay, what is 12 volts over E? What is 12 divided by E? E to the power of 1.
4.414.
4.4. So from 12 volts to go to 4.4 something volts, it'll take 12 seconds for those to for that resistor capacitor combination, right? So for this, if I'm going to say, suppose the initial voltage, the starting voltage is 12 volts, and the voltage after a period of time is 1 volt. The voltage after a period of time is 1 volt. How much time has elapsed? Okay? How much time elapsed if this is the case? So again, the voltage initially is 12, and after draining out for some time, it is 1 volt. How much is the time? How long did it take for the voltage to go from 12 to 1? To drop from 12 to 1, how much time did it take? So for that, you just have to use that equation. So it will be like V equals to V naught e to the power of minus T over RC. And then I gave you the answer. 1 here is 12 times e to the power of minus T over 12, right? Is that right? 12 is the seconds. RC is the time constant, so I know that number, 12. Now we just have to solve it. So 1 over 12 is equal to e to the power of minus T over 12. Or flip this, you get 12 is equal to e to the power of T over 12. So I just flipped it. It became positive. Now what you do from here is take natural log on both sides. Take natural log on both sides. What do you have then? Natural log of 12 is equal to T over 12. That's it. Because natural log of E is 1. So how much is the time? 12 times natural log 12. Tell me the answer.
.82 or 81.
Okay, 29.8 seconds. So you know the time constant is 12 seconds. But for it to discharge from 12 to 1, it takes 29, almost 30 seconds. Almost 30 seconds it takes for it to drain to 1 volt. 12 seconds it takes to drain to 1 EF of it, like to bring it down to 37%. It takes only 12 seconds. But after that, it goes on. For it to go up to 0.1 volt, it will take forever, a long time. If this is going to be 0.1, this is going to be 120, so len 120, right? So if it is len 120, can you do that? 12 times len 120. How long is that?
12 times what?
12 times len 120. Because I'm saying if this is 0.1 volts, not 1, then it's going to be 0.1 here. So 0.1 over 12. So 12 over 0.1, that is 120.
So 57.47.
What's it? I thought it's more. Are you sure?
That's what I got.
57.
No, len 12 times 12.
Oh,
Yeah, len 120 times 12.
yeah.
Yeah. 57.
That sounds true.
57.
Yeah, possibly, yeah. That's possible. Because every time it's going by 63%, so that's... Alright, so you saw the discharging. Even in the case of charging, you do the same thing. Now, if the question was about current, how much is the current going to drop? Same thing. You already have the same equation. I is going to be I naught. Maximum current is I naught in the beginning, times this. So the discharging is going to take place according to this. So what is the secret of RC? RC is the time constant. In fact, an RC circuit is used in circuitry mainly for time control, to control the timing. In fact, RC is a timer. It is a timer. Okay, so if I actually connect the capacitor to a resistor and charge the capacitor fully to a certain voltage and let it discharge through this, after some time it will become like, after one time constant, after 12 seconds it's going to be like, from the highest voltage I gave to it, it's 63% lower. And after some more time, it's going to be lower than that. So the voltage will keep dropping. Now you can actually like make a circuit work until the voltage goes down to a certain value. Now what if I put this one as 600 kilo ohms? What's the time constant? If I put 600 kilo ohms, it's just a resistance, 600 kilo ohms, which I have there. I have this and I have this. 600 kilo ohms is not a big deal. So if I have 600 kilo ohms and 2000 microfarad capacitor, and if I connect them into a circuit, how much is the time constant? How much? 1200 seconds, which is how many minutes? How much? 20 minutes. So it's like 20 minutes it takes for it to become, like if you start from 10 volts, it'll take 20 minutes for it to drain down to 3.7. Make sense? From 10 volts to 3.7, it'll take 20 minutes. So if I have a circuit which will function if the voltage is more than 5, then from 10 to 5, however, how much time is that going to take? Of course, it's going to be less than 20 minutes, right? So maybe 15 minutes, something like that. So this circuit is going to be active for that much time. And after that much time is over, it's over. It stops. Those are timers. That's a timer, actually, that's a timer. And we use those timers in different places, right? Like automatic doors. You just walk next to it, it unlocks. You can hear the click. Do you hear the click? It unlocks. Once it unlocks, you're able to freely open the door. Anybody from the other side also can open the door because it's unlocked already. Your presence there immediately sensed, and then it unlocks the door. But after that, you went to the other side. Does the door immediately lock after you close the door? There's a period of time. That's called a time delay. And what is causing the time delay? RC circuit. The resistance capacitance combination, which is in the circuitry, is what delays it. Now you can make it delay this much. You can make it delay 12 seconds, but I don't think they delay that much. I think it's just a couple of seconds. 1 or 2 seconds and it automatically locks it. Because as soon as you close the door, immediately push it open, it will open up. Because it's still open. And then after a couple of seconds, you try it, it will be closed. So automatic doors, they use timers like this. So yeah, this is a good application. If you want something to stay on after you, like your cars, the dome light of a car, right? You open the door, you lock the door, the dome light is still on. Or some lights are still on. And you'll be like, okay, is that going to go off by itself? Yeah, that dome light is on because suppose you just unlocked it. I mean, you locked it and then just you wanted to like look inside if you forgot something. Yeah, you have it there. Light is there. You don't have to unlock it and then get inside to check it. So you see already there. The light will stay on for a period of time and then slowly fade off. Some of them like go abruptly off if it's a cheaper one. And if it's a better car, then it goes fading off gradually. Timer. What about your security lights around your home? Does it have a timer? Yeah, you can see, you can set it as well. What are you setting? What are you turning? You're turning this. What are you turning there? You know those little things to turn? What are you turning? To make it more time, you're increasing the resistance. To quickly turn it off, you reduce the resistance. That's it. So that unit contains capacitors, that unit contains resistors, and the resistor is the one which you are actually controlling to make it turn off. And there's another button which is for sensitivity, right? How sensitive you want it to be. Now, if you make it very sensitive, then it kind of, the sensitivity is so strong that even any car goes on the street, this will come on. You don't want that. You don't want this thing to come on when there's somebody is driving on a car on a street. You don't want this thing to be on. You want it to be on only when someone comes in that circle. So you reduce the sensitivity to the required value so that it won't come on and off every time. If your sensitivity is too much, every time the branches of a tree like moves like that, it's on. If it's a stormy day, you'll see these things are coming on again and again because there's something moving in front of it. Right? So reduce the sensitivity, and that's one. This is the other one. This is what we normally control more, because how long do you want it to stay on after it turns on in order to save power? You want it to be turning off not too long after, not 20 minutes. That's too long. You're wasting so much electricity. So you want it to turn on, and maybe a minute after you want it to go off, then set your resistance accordingly. Yeah.
Is that the same thing like the video doorbells? Have you ever seen those like
Video doorbells? Yeah. Like it turns on the camera and all those things. Yeah, they're all anything to do with timers, anything to do with timing. It automatically times something. That is an RC circuit. RC is basically the timer. Well, you can build things to destroy. You can actually construct something constructively or destructively. The same timer. What is that?
Time bomb.
Time bomb. A time bomb is just RC again. So you play with R and C, and then you can create a time bomb which will activate 1 hour after, 24 hours after, depends. Okay, so if you know particularly that the meeting is going to start at this time, and the guy is going to be speaking at this time, so you want to finish him off. Okay? Thinking in terrorist mindset. Of course, we have to think, You got to think in their language. Then only you'll be able to stop them from doing it. You cannot be so innocent, right? So how is it? Like for example, if I'm trying to catch somebody who's making a mistake, I need to think in his lines. What could potentially happen, and then after that, catch. So you need to really spy on that one. So a thief knows another thief's mind. You know what I'm saying? So another thief knows very well what the other thief is going to do. But innocents will not know anything. Innocent people will not have an idea that this is a thief or that's not a thief. We will be so blank. Only when we are a victim, then we'll understand something's going on. Well, these days there are lots of security features that you can actually add to, like for example, the Kroger shootings. Can those be protected? Can those be prevented? Very much. Because, you have scanners on your doors to find out if you're taking a small button outside without paying for it. Right? You can detect that. And you cannot detect a gun coming in. Weird. You know what I'm saying? A small thing that you bought. No, you didn't buy. You just picked it up. So, for example, there was some little thing, and I just put it in my pocket because I didn't know. Maybe a pen. I bought a pen. Okay, it's $3. Looks good, but I didn't have a card, so for the time being. And then when I went to pay, I forgot about it. I forgot about the pen in my pocket. Okay, so I just go on. And after that, I pay. When I'm going out, beep, beep, beep. What is happening? And they'll come and check. Oh, yeah, I forgot this. This is here. Now, if you can do that, why can't you just put scanners, kind of body scanners, as people cross into the entrance, and then have someone supervise the entire thing on a screen, and you'll see the gun going. As soon as you see the gun going, get some people like Adam and just bring them down. Right? Because he won't have any idea that this is going on. He won't have any idea that this is going on. So you see that. So It's very important that you have to supervise. You have to, like, somebody has to take care of such a big place, and this is happening again and again. These days, happening more frequently.
Yeah.
So at least one person can, or the manager can actually have this camera system that's like being scanned. And so when you see a metallic object, especially a gun, it is definitely visible. It's definitely visible. You know, at the airports, they are scanning it so well. When I was coming this time from India, I had something called, it's called M-Seal. M-Seal. It's a kind of glue, okay? I think I have it here. M-Seal. Let me check. There it is. It looks something like this, but it is not that. It's a useful glue because it's so strong that I don't find it anywhere here also. It's very, very, very strong. That, you know, it's got two things to be added into it and it will become like a black object. And that, it is pretty squishy initially. And you can actually stick anything you want. Anything you can stick. If I put a little bit over here and stick it there, I cannot just take it out. You try as best as you can. Metal, it's glued. Now, if I want to drill a hole, I need a drill actually. I can't make a hole in that. So it's so strong. I frequently use them, that kind of a glue. So I bought 2-3 packets. No, I bought 4 packets actually. 4 packs of them. And while coming from India, at the airport in India, I'm just checking in the bags. Now, before I check the bags, it has to go through a scanner. So it went through the scanner, and they will actually, put a security tag on it saying secure, and then it is going. I don't see it happen here. I don't see it happen here. Strangely.
I think that happens like where you don't see.
Where?
Well, I think like because you're talking about like your checked luggage.
Yeah.
Well, because like you go and like they register that, but I think they check it elsewhere.
Elsewhere? Never seen that. Because I've carried lithium batteries and nobody said anything. And then when I read something elsewhere, this time I wanted to take a drone. And then someone said, oh no, I don't think drones are, you need to remove the lithium batteries and put in your carry bag, not in your checked baggage, because lithium batteries can explode. I've taken so many lithium batteries before in the checked baggage. And then I'm thinking like, okay, then why didn't they find it out? Why didn't they find it out? So I didn't take the drone this time at all because it was a cool drone. It goes by your gestures. You've seen those? That's a beautiful drone. I have it. I need to study how it works properly. Then only I can use it properly. Because right now it is like, you keep it in your palm, know the remote controls, right? So I just keep it in my palm, turn it on, and then it starts on, and I just release it like that. It just stays in front of me. It just stays with a certain height in front of me. And it looks at me, the camera is kind of looking at me. And if I move like that, it looks at me and it turns around. So it kind of recognizes me. And once it recognizes me, I'll put my hand like this, it recognizes my hand. Then I do that, it'll start rising. And when I bring it down, it comes down. And if I say bye-bye, it just goes, whoosh, it goes off. And it stops somewhere far away and stands there. And then I do this. I do this, and I can see it flashing because it's going to take a picture and then it posts. And it takes a picture of you. That's a cool thing. And then after that, I stand like this, and it's waiting for my command. It's looking at me from a height. It's looking at me like this, and then I'm standing there and saying, when I do that, I'm giving instruction for it to take a video of me. When I do that, I can see it blinking, and after that, the video started. Once the video started, I can run, it'll follow me. It just takes video and keeps following me. And wherever I go, it's actually tracking me, and taking a video. So if I'm going to ride a bicycle like that, I can keep riding the bicycle, and it's going to take a picture of me, video of me as I drive, and it's taking it. Now, if there are obstructions, it will manage it by itself. There are further, commands about it. So, yeah, that's the video part of it. It's cool. But I have to really understand how to manage it and all those things, and then only, and it can actually go to 500 feet and all that so easily.
Under what?
500 feet. 500 feet.
Oh, fine.
That's a lot of distance. And then, the best part is to bring it back. How do you bring it back? It's already gone that far. How do you bring it back? Simple. I have to do this, and it senses that I'm calling it back, and it beautifully comes down. First it kind of comes straight like that, and then drops off, and then once it comes to a level, it starts coming to me, and I'm going, will it stop? I am afraid that it's going to come straight to me. And believe what? Where did it go off from? It comes to the same GPS spot, same spot. And once it comes there, it stops and waits for my instruction. Then I just put my hand under it. It senses that I'm calling it onto my hands. It just comes down, settles, and turns off immediately. It's beautiful. Well, that being said, drones are going to be pretty dangerous too. In future, drones are pretty dangerous. In fact, the military, they're going to use drones to, you want to see?